Hi everyone, this is the course EC657A. The course instructor is Professor Mark Crowley. I am Benyamin Ghojogh, the TA and presenter of the slides. And this is the lecture on Fisher discriminant analysis and linear discriminant analysis. In this lecture, we are explaining both Fisher discriminant analysis and linear discriminant analysis, and we say how they are related. Okay, here we show the notations of data set. Assume we have some training data set, some training data points. Each data point, training data point is denoted by xi, which is d-dimensional. D is the dimensionality of data, and assume we have n data points. So we have I from 1 to n. And we columns, the vectors are column vectors, and we put the if we put the column vectors column wise in a matrix, we'll have X as a matrix of data set, which is d by n. Here we are supervised, so we have labels of classes. Therefore, assume we have C classes. J goes from 1 to C. J is the index of class, and we show the ith sample of jth class by xi superscript j, which is also d-dimensional, and nj is the number of points in the jth class. The mean of training data, we show it by mu x or mu, which is the average of data points, and the test data set, we have also a test or out of sample data set, which is not used for finding or training the projection matrix in Fisher discriminant analysis, and we call it xti, which is the ith test point in the test data set. We assume we have nt test data points, and we put them column wise, and we call them xt capital T, x capital T, and which is d by nt matrix. In Fisher discriminant analysis, we have inter-class scatters and intra-class scatters. The scatter is kind of another name for variance. So we have variances. And let me tell you why. Who was Fisher? Fisher was the one who proposed Fisher discriminant analysis, Ronald A. Fisher, and he proposed a lot of things in statistics and machine learning, and that's why the whole modern statistics owes him. He proposed variance. Can you imagine statistics without variance? And there's no wonder why we see that Fisher discriminant analysis is all about variances. He also proposed several other things like ANOVA. The famous iris flower data set is proposed by Fisher in the same paper which proposed Fisher discriminant analysis, and he was a scientist in genetics, and these things like Fisher discriminant analysis and these things were first used in genetics. So here in equation 5 is the mean of the jth class. So we take the average of the data points in the jth class. Mu is the total mean, which is the total mean, or which is equivalent to the weighted average of the means of classes. SB is the between scatter, and SW is the within scatter. Between scatter, or also called inter-class scatter, is the scatter of variance between classes. SW is the within scatter, which is the scatter of variance within classes. So SB is the variance between classes. What does it mean? Assume that here is the total mean. Here we have mu1, mu2, mu3, and this is the cloud of points of third class, the cloud of points of the first class, the cloud of point of the second class, assume, and this is the total mean. So SB calculates this. How far the classes of the means of classes are from the total mean, or in other words, how far the classes are from each other. So the farther the classes are from each other, the more SB we have. SW is the scatter or variance within classes. So the more spread each of these classes are, the more SW we have. So SW is the variance, the summation over classes, but this is the variance of each class, how spread the cloud of each class is. And we are going to use this. Before that, I'm going to tell you what projection is, because Fisher discriminant analysis uses projection. The reason is that's why it's a linear method, because it uses a linear projection. So we have x, and x breve here is the center data. Although we don't need center data, we don't need to center data in Fisher discriminant analysis, but for some reason, for explaining why it is, for explaining what this means, U transpose SU, I'm using x breve here. And then I told you that there is no need to center data. U transpose X is the projection of data. And if we have a projection matrix, U transpose X is the projection of X onto the column space of U. And what is the column space of U? It is the space spanned by the columns of U, or the space whose basis vectors are the columns of matrix U. And what is U transpose? It's just reconstruction of data. And we show reconstruction of data by X hat. And before that, we denote projection of data by X tilde. So U transpose X is X tilde, and X hat is U transpose X, or U X tilde. And what is projection and reconstruction? Let me show some figure. Assume that I have a two-dimensional data, and assume this is a projection direction, one-dimensional. If I project this data point X onto this projection direction, it is this. So if it is P, if it is assume this is one circle, two circles, so this is the coordinate of one circle, two circle, and this is the projection direction P. In one-dimensional projection direction, this is X tilde, which is one-dimensional. The X itself is two-dimensional in the coordinate of one circle, two circle, but X tilde is one-dimensional in the projection in the subspace of P. However, if we show this X tilde in the coordinate system of 1 and 2 again, which is this, here we had P, which is this is called X hat, which is two-dimensional. So we'll have some reconstruction error. So this is the concept of projection and reconstruction. And as you can see here, we are showing that the squared L2 norm of reconstructed data, what is it? If I replace U transpose X breve here, and here we are using a formula, you can have this from me, X transpose X, if X is a vector. We are using this here, so then you can see that we apply this transpose onto this parenthesis. However, when we apply the transpose, the order is reversed. So it's X breve transpose U transpose U transpose X breve. And as the projection, we assume that projection matrix is an orthogonal matrix, or in other words, the projection directions are orthonormal. Therefore, U transpose U is 1. So we will have these two, and as these two are scalars, we can in multiplication of scalars we can change the order. We change the order and we'll have this. And what is this? We put, let's assume we put some summation over n data points here, and we use this here. And as u is independent of, is not a function of I, it can be come out of sigma. And what is this? What is this? This is projection. This is covariance matrix. This is covariance. This is the definition of covariance matrix, because the covariance matrix is defined as xi minus mu transpose, which is d by d, and we denote it by s. So we say that x, the squared Frobenius norm of reconstructed data, or the squared L2 norm of the reconstructed data. Frobenius norm is somehow like L2 norm for matrices, is equal to u transpose su. Here we had u transpose, this is s and this is u. So now, or the squared L2 norm is u transpose su, or if in matrix form, it this has a trace. This has a trace because we need to have a scalar variance. That's why we use trace. And trace is the summation of eigenvalues, and this captures the variance of data. Just give me a second to. Okay. Now, as I said, this is projection into the p-dimensional subspace u transpose x. We denote it by x tilde, and the reconstruction is u transpose x plus mu x, or this. But here, as I said, in Fisher discriminant analysis, we don't need to center data. That's why we can ignore these mu x parts. In test projection, we project using the projection matrix which we found in using the training data. And what is this? Is this figure? It says that if I have a point x, which is d-dimensional, I can project it onto the column space of u, which is p-dimensional, or p. P is less than or equal to d, and usually it's much less than d. And then if we represent the projected data in the d-dimensional space, that's the reconstructed data x hat, and we have a reconstruction error. What is the goal of FDA, or Fisher discriminant analysis? It's just, it wants to separate the classes more. How? It says, assume that we have in figure 1, we have some data points, and we have two classes, circles and crosses. We want to separate them more. How? What we can do? We can say that let's make the classes farther from each other. So I put the crosses away, and I put the circles away. Then in the third figure says, okay, still we can improve this separation. How? By reducing the variance of each class. So the class was like this, we reduced it to this. The class was like this, we reduced it to this. So here we are increasing the between scatter. Here we are reducing the within scatter. I have an example. I've made an example which is, I think, explains this better. For example, I have some problems with my eyes. Assume, and I am both colorblind and my eyes are also weak. There are some blue and red balls, and on the ground. I want to separate them, but it's very hard for me to separate them because my eyes are weak. Also, I am colorblind. So how do you help me? You assume you are a Fisher discriminant analysis and you want to help me separate these classes, these balls. How do you help me? Consider my first problem, which is color blindness. What do you do? In order to help me, you can separate the blue classes from red classes a little bit, like in figure 2. You increase the between scatter. And then still my eyes are very weak. I cannot see the balls very well. my second problem of my eye. And then what do? You say, okay, so now I put the blue balls next to each other, so you see them as one ball because your eyes are weak, and I put the red balls close to each other so you can see them as one other ball. So you are as in figure 3, you are reducing the within scatter. So Fisher discriminant analysis, the goal of the FDA is to increase between scatter and reduce the within scatter. And I can tell you that all supervised dimensionality reduction methods usually have this idea. So they all, in different ways, they all do this in order to separate classes. For example, like many different things, like in triplet loss or metric learning, even using in neural network based dimensionality reduction, when they are supervised, they usually do this. They increase the between scatter and reduce the within scatters. And it was proposed, as I said, by Ronald A. Fisher, who was alive in these years, and the whole modern statistics owes him. So what is the optimization of FDA? As I said, we define a Fisher criterion, which is the trace of U transpose SBU over trace of U transpose SWU. And why is this? As I said, we want to, in this slide, I said we want to increase the between scatter, so it is on the numerator of the Fisher criterion. We are maximizing this Fisher criterion. So the numerator is maximized, and the denominator, which has SW, is minimized. Therefore, as we want to SW to be reduced, we put it in the denominator, and we are maximizing the whole Fisher criterion. And why are we using trace of U transpose SU? Because I explained it here by equation 12. I said that trace of U transpose SU somehow shows the variance of projected data or the squared L2 norm of the reconstructed data. So it says that I want to maximize the between variance of projected data while minimizing the within variance of projected data. This when we only have one projection direction, which is U, this is called a Rayleigh-Ritz quotient. Rayleigh-Ritz quotient. And when we only have one projection direction, the Fisher criterion becomes this. We don't have trace anymore. In that case, when we have only one projection direction, this maximizing this is exactly equivalent to maximizing without trace. So maximizing U transpose SBU subject to U transpose SWU equals a constant like 1. The proof can be found in our tutorial paper on FDA. However, here, as we have several projection directions, we can approximate it with a good approximation that this is approximately equivalent to this. So we say we maximize the numerator while we say that the denominator is equal to a constant. Here is I, for example, identity matrix. And we want to solve this optimization problem. How? We write the Lagrangian. What is Lagrangian? Lagrangian is so easy. If you don't know it, I explain it to you. Don't worry about it. It just says that, do you remember your optimization in high school? In optimization high school, we had an unconstrained optimization problem. How did we optimize an objective function? We just take the derivative and set it to 0. But here we have constraint, and this constraint is a pain in the neck. How do you do that? So you say, okay, let's have the Lagrangian. What is the Lagrangian? It says that this is the objective function, and we penalize the constraint somehow with some weight. This weight shows how important is satisfying the constraint with respect to or compared to the objective function, which is trace of u transpose SBU. And this parameter is usually called the dual variable, this weight parameter. So the dual variable. And then, so we now we as it is a maximization problem, we maximize this Lagrangian. Again, this has reduced to the high school optimization. It's an unconstrained optimization, so let's take derivative and set it to 0. When we take derivative, this is a quadratic form, so it is 2 SBU its derivative, and the derivative of this is SW u lambda, and when we set it to 0. And why is it d by p? I have explained it in the lecture of PCA, but I briefly explain it here too. So when you take derivative of a scalar with respect to a scalar, the result is a scalar, the derivative. Why? Because by tweaking the second scalar, the first scalar also changes. This is the interpretation of derivative. The derivative of a scalar with respect to a vector is a vector. Why? Because when you tweak every element of the vector, the scalar changes. A derivative of a scalar with respect to matrix is a matrix. Why? Because when you tweak every element of the matrix, the scalar changes. The derivative of a vector with respect to another vector is a matrix. Why? Because when you tweak every element of the second vector, every element of the first vector also changes. The derivative of a vector with respect to a matrix is a tensor, a 3D tensor, a 3 tensor. Why? Because when you tweak every element of the matrix, every element of the vector also changes. So here we have a scalar Lagrangian with respect to a derivative with respect to a u per a matrix. It is a matrix, and when we set it to 0, when easily we put this in the other side of equation, and we have this. And what is this? You had seen that, so it was SBU u lambda. What is this? This is just an eigenvalue decomposition or eigenvalue problem. However, we have SW here. When we have SW here, this is called a generalized eigenvalue problem. If you want to know more about eigenvalue and generalized eigenvalue problems, you can see our tutorial on these topics, on eigenvalue and generalized eigenvalue problems. So the solution of FDA is a generalized eigenvalue problem of SW. They write it in this way. We can change this generalized eigenvalue problem to an eigenvalue problem, but how? By left multiplying SW inverse. And so this is the eigenvalue problem for SW inverse SP. It means that the projection directions of Fisher discriminant analysis, or U, are the eigenvectors of SW inverse SP, and lambda here is the eigenvalues. But sometimes SW is singular, and for that we usually strengthen the main diagonal of SW. How? By saying that we replace SW with SW plus lambda or epsilon I, where epsilon is a very small positive number, and this makes SW usually invertible and non-singular or full rank. However, it reduces the accuracy, or it just approximates somehow. This is a trade-off. And then let's talk about the dimensionality of the Fisher discriminant LDA or FDA subspace. What is the rank of SW inverse here? What is the rank of SW inverse SB? Rank of multiplication of two matrices is less than or equal to minimum of the ranks of those matrices. So less than or equal to minimum of rank of SW inverse, rank of SB. What is rank of SW inverse? What was SW? Do you remember that? Rank of SW inverse is equal to the rank of SW. And what is that? This was SW. Equation 8. it says that, okay, this is SW, and you see that we have summation of over classes and over the samples of classes. So it's like somehow reduces to summation of, sorry, what happened? This is the summation of over the whole data, somehow reduces. So we have summation over the whole data, and because we have summation over n data points, the rank is minimum of n. Here you see minimum of n minus 1. Why is n minus 1? Because one assume that we have only one data point. The rank is 0. That's why, because of this special case. So the rank is n minus 1 because of this summation that I told you. Also, the dimensionality of SW is d by d. So the rank of SW is minimum of d and n minus 1. What is the rank of SB? The rank of SB come here. We have summation over C classes, so, and it is d by d matrix. So the rank of SB is minimum of C minus 1. Again, I told you the reason of minus 1, because when we have summation over something, the rank is minimum of the dimensionality of that matrix and that minus 1, that the number of iterations in summations minus 1. So it is, here we have minimum of d and C minus 1. We combine these means together, so we have minimum of d n minus 1 and C minus 1. Usually the number of classes is much less than the number of points and the dimensionality, so it's usually C minus 1. That's why the dimensionality of Fisher discriminant analysis is usually at most C minus 1, one less than the number of classes. And so when we have U, which is d by d, we should truncate it to U d by p, where p is at most C minus 1. The other ones are usually invalid, the other ones. And what this is after sorting from largest eigenvalues, sorting the eigenvectors by largest eigenvalues to the smallest eigenvalues. Why? Because we are maximizing. If we were minimizing, we would sort from smallest to largest. Here we should sort from largest to smallest. What is the relation between PCA and FDA? You can see that FDA finds the direction on which the classes are separated more, although PCA finds the direction on which the variance of data is at most. Here in figure A, the FDA and PCA directions are orthogonal on each other, because FDA here, when classes are projected on this, they are separated. However, FDA finds the most variant direction of data. Here in B, PCA and FDA directions are equivalent. Why? Because FDA finds when the classes are projected on these two, they are separated. Also, PCA finds the most variant direction. Here, they are neither equivalent nor orthogonal, so we can have different cases. Now we switch to LDA, linear discriminant analysis. Fisher discriminant analysis is over, and we'll tell later what is the relation between these two. So what is LDA? Assume that we have two classes, each of which has a Gaussian distribution, n mu1 sigma 1 squared and n mu2 sigma 2 squared, and each of them have a mean. We want to find the x star where the classes, this is the boundary, because here we have more probability for class 1, here we have more probability for class 2. Here is the boundary x star. We want to find this boundary. So LDA is for classification. FDA, that I explained before, was for subspace learning, or was for dimensionality reduction or feature extraction. But however, LDA is for classification. We want to classify these two classes. We want to find the boundary, the classification boundary. What is the P of probability of error? It is that if the point is already in class 1, however, we x goes after, x falls in this region, is after the boundary. Plus, if the point is in class 2, really it is in class 2, although it falls in the region 1. So, and what is, we know that if P is in class, x is in class 1 and x is less than C, it is CDF of C, class 1. This is the definition of CDF, a cumulative distribution function. P here P is probability density function, F1 is the cumulative distribution function. And if P x is in C2 and x is less than x star, it is the CDF of class 2 on x star. Here we also have here, according to the, also have if P is x is greater than x star, not less than, it is 1 minus CDF, because this is CDF, this part is 1 minus CDF. Then let's replace these in this formula. But before that, let me tell you that this prior, that if x is in class 1, we call this by pi, we denote it by pi 1. The prior, if x is in the C2, we denote it by pi 2. If we replace all of these in this formula, what is it? We will have this 1 minus, give me a second for my pen, there is a problem with my pen. Okay, we will have 1 minus this, as we had here, pi 1 f2 pi 2. We want to minimize the probability of error, where the objective variable is x star. So when we want to minimize this, it's an unconstrained optimization problem, high school optimization. Take derivative and set it to 0. When we take derivative of this is a constant. Here the derivative of CDF is PDF. So minus f1 x star pi 1 plus f2 pi 2. We set it to 0. This is the solution. And usually, as I said, in LDA, we assume that the PDF or small f is a Gaussian distribution. Equation 24 shows the Gaussian distribution, a multivariate Gaussian distribution. In general, it is a multivariate. And then let's replace this equation 24 into equation 23 to have this. So when we have this, let's solve it again. So now in LDA, also we assume that sigma 1 here, used here, and sigma 2, sigma 1 is here too, sigma, they are equivalent. So we assume that, for simplicity, we assume that the covariance matrices of classes are equal. If we don't assume that they are equal, it will be quadratic discriminant analysis. For more information about quadratic discriminant analysis, you can see our tutorial on linear and quadratic discriminant analysis. But here in LDA, we assume they are equivalent. So we put them as sigma in this formula. We replace sigma 1 and sigma 2 by sigma, and we will have equation 26. So these two terms are cancelled, and we only have exponential terms and pi terms. So it will have equation 27, which is repeated in equation 28. Then let's take log or ln, natural log, from the sides. We'll have this equation 29 and 30. So then, okay, let's simplify these terms. Assume what here, x minus mu 1 transpose sigma inverse x minus mu 1. So if I have this transpose, if I apply it on the parentheses, it becomes like this, and then if I multiply the terms, we'll have x transpose sigma inverse x minus x transpose sigma inverse mu 1 minus mu 1 transpose sigma inverse x plus mu 1 transpose sigma inverse mu 1. And then you can see that these two terms, okay, this comes here, this term comes here, and these two terms are just both a scalar, so I can replace x transpose sigma inverse mu 1 by mu 1 transpose sigma inverse x, and I add them together. Well, I will have this. So we saw that we have this, we found this in the previous slide. Let's replace this in equation 29 and 30 in this equation. If we replace that, we'll have equation 32, and if we simplify the sides, just we bring it in on one side, and we just take factor out and all this, and simplification just gives equation 33. This is the equation for the boundary of LDA. So the x's which satisfy this equation equals to 0 are the points on the boundary, and it is a linear boundary. And why is it a linear? It is a linear boundary because it's exactly an equation for a linear equation. It is a linear equation. This is the slope, and these are where it intersects. So this is the slope, and this is the intersect. So we denote the boundary by delta x in equation 34, which is a repetition of equation 33, but it doesn't say equals 0 because we want to say it is the boundary. And if the delta x is less than 0, it is on the left side of boundary, which is in class 1, which we say that our estimation of x is in class 1. If it is on the right side of the boundary, it is on class 2, and if it is 0, it is boundary. Now assume we have multiple classes rather than binary classes or two classes. Do you remember we had f pi? Here we had f pi. In equation 23 we had fx pi. Now assume for the kth class, consider you have fkx pi x, and if we only consider this, if we take ln or natural log from this, we will have this term, and delta is considered to be, this is a constant, so we get rid of it, we don't care about this. The summation of these terms we denoted by delta kx. In order to estimate or predict the class of a point, we say that whatever, because we have delta 1 until delta c, we have c classes, whatever k that maximizes the delta determines the class of class. For example, the class of that x. For example, the x will give me several deltas, like for example, assume this is 0.1, 0.5, and one of them is 0.8, and all of these, and the largest one is 0.8. So this is the class of the last class is the largest, so x is in the last class, something like that. What is the relation of FDA and LDA? And as I told you, FDA, Fisher discriminant analysis, is a linear method. However, it's for dimensionality reduction and feature extraction or subspace learning. But LDA is for classification. But they are related. How? Consider this. We define the distance metric as this. We denote it as this. What was before that? Let me tell you. This is Euclidean. Do you remember? This is x minus mu, x minus mu, x minus mu transpose x minus mu. This is Euclidean distance between x and mu. This is Euclidean distance. But we can generalize it, or a squared Euclidean doesn't have this. This SQRT. This is a squared Euclidean distance. However, we can have Mahalanobis distance. What is Mahalanobis distance? Mahalanobis distance says that assume I have two classes, two clouds of points, or two classes. These are the means of these classes. This is a cloud second. Okay, this is class 1, this is class 2. Consider this point. The distance, the Euclidean distance of this x from the means of these two classes says that this distance is smaller, so x is predicted to be in class 2. However, someone named Mahalanobis, which was a statistician, said that x can be intuitively x must be in class 1 because it is closer to the cloud of data in class 1. Although its Euclidean distance to class 2, to the mean of class 2 is smaller. So it says that we should somehow weight the Euclidean distance. How? We add sigma inverse in between. So it will be x minus mu transpose sigma inverse x minus mu. Why? Because he said that we should weight in the way that the more variance a cloud of data has, the less its distance must become, because this x is closer to the cloud and the cloud is large, so this distance must be less, must be considered less. That's why it has inverse, sigma inverse. However, this point is not far from that class 2 because the cloud of class 2 is small. This is Mahalanobis distance, and then we can have a generalized Mahalanobis distance where we replace sigma inverse by a positive semi-definite matrix A. Why should it be a positive semi-definite matrix? Here we have A. Because in order to, if A is positive semi-definite matrix, this distance just satisfies the triangle inequality, and it is also convex. Without satisfying triangle inequality, it won't be a valid distance metric. So as it is a positive semi-definite matrix, we can write A as UU transpose, and then we can replace A with UU transpose here. According to the definition of positive semi-definite matrix, we can write A as UU transpose, and then we put U in these parentheses after applying this transpose. We also put this U transpose in this parentheses. We will have this. Now you can see that we have this. This is, what is this? Equation 42. It is the Euclidean distance of projected data. So it's like applying Euclidean distance after projection of data by projection matrix U, which is U transpose X. So we can say that the generalized Mahalanobis distance is like applying Euclidean distance after projecting data. And also, do you recall that in projection we have, when we project data, its mean is also projected. However, according to the quadratic characteristic of variance, it's the variance of projected data becomes U transpose sigma U. And do you remember in Fisher criterion we had the between scatter in numerator and then within scatter in denominator. So the between scatter between classes are U squared, because the quadratic here we have quadratic characteristic of scatter. So U transpose mu2 minus U transpose mu1 squared, and in within scatter we have U transpose sigma 2 U plus U transpose sigma 1 U. Assume we have only two classes here, because in LDA at first we assume we have two classes, and then we factor out U transpose, and we will factor out sigma 1 U transpose and U. We'll have this. Then in Fisher discriminant analysis we maximize the Fisher criterion, which we found also here in equation 44, and we said that this is a Rayleigh-Ritz coefficient. I explained it before. It is equivalent to this. Then we take Lagrangian and we take derivative, we set it to 0, and when we will find out this. And as you can see, the projection direction U in Fisher discriminant analysis is the eigenvectors of sigma 2 plus sigma 1 inverse, because this is a generalized eigenvalue problem. We can convert it to the eigenvalue problem by left multiplying the inverse of within scatter. Do you remember we had it here? We had it in equation 21. So here we can have this, and we can say that U is the eigenvector of sigma 2 plus sigma 1 inverse mu2 minus mu1 here, as we have here, mu2 minus mu1 transpose. So we have this, and now we found this. In LDA we said that mu1 and mu2 are assumed to be equal, therefore we can write it. This is simple. Equation 50 is simplified to equation 52, and we can say that U transpose X so is, this is U, this was U, so U transpose X will be this transpose X. And now compare equation 53 with equation 34. What was equation 34? Here we had in LDA. So here we have some projection, sigma inverse mu2 minus mu1 transpose. Here we also have this with some but this is quadratic. That doesn't matter, it's just up to a scale. So rather than having one term, it's just squared, and we can say up to a scaling factor, therefore these are equivalent. LDA is equivalent to FDA. Although LDA is classifier, FDA is subspace learning. In other words, LDA projects onto a subspace and then classifies using Euclidean distance. FDA projects onto a subspace, and if we apply FDA and we use Euclidean distance, it is equivalent to LDA. We also show you some examples, like here we have Fisher faces. What is Fisher faces? When we apply FDA on face data set, we will have some directions, projection directions U. Do you remember U was D by P? So the columns of projection matrix are d-dimensional. If the projection directions are d-dimensional, we can reshape them into the picture form again, and we can see we'll see some weird faces which we call like ghost faces. These extract the features, and as you can see we can have ghost faces in both FDA and PCA. here these are called Fisher faces, those are called eigenfaces. If we compare those, here for example an oral face data set we apply, and you can see that the Fisher faces extract the features which discriminate the classes, like the eyeglasses or the hairs and these things. However, the eigenfaces extract different features which show the variance of data. So these are different characteristics of FDA and PCA found. And also we can have reconstructions by FDA and PCA. However, reconstruction in FDA is not good because it's not used for reconstruction. Although in PCA optimization, I explained in the PCA lecture that is the best linear method for reconstruction. It's according to its optimization. Therefore, you can see PCA using all is reconstructed very well, although reconstruction in FDA is not good. And PCA using only 3 is reconstructing well enough, but not perfectly. Using 3 eigenvectors, I mean. This is an example for LDA with 2 classes and with 3 classes. And as you can see, the boundaries between classes are linear. There is also one thing that I want to tell you, that we have proposed, this is our own proposed method, Royce discriminant analysis, named after Sam Royce, to whom manifold learning owes a lot. It generalizes subspace learning methods based on generalized eigenvalue problem, which we also saw in Fisher discriminant analysis. It says that we have a Royce map, which whose corners are the special cases already existing in the literature. Here we have PCA, here we have FDA, here we have supervised PCA, which we didn't explain, and here is double supervised discriminant analysis, which was not proposed and it is novel. And we have a continuous map where we have 2 Royce factors R1 and R2. When we play, and R1 and R2 are between 0 and 1. When we are here in the left corner, we are completely unsupervised. When we are here, we are completely supervised. We use labels twice. And when we are in these corners, we use labels only once. So we have a Royce map where coming from this corner to this corner, the supervision level increases. And we can also have this Royce map in the feature space where we have kernel PCA, kernel FDA, kernel supervised PCA, and kernel discriminant. The double supervised discriminant analysis are the special cases. You can read our paper for more information. These are some useful resources to read. A tutorial paper we have on linear and quadratic discriminant analysis, a tutorial paper on Fisher and kernel Fisher discriminant analysis, a tutorial paper on eigenvalue and generalized eigenvalue problems, and some YouTube videos which is very good by Professor Ali Qudsi at University of Waterloo. These are the references. This is the original paper by Fisher, which proposed FDA. Also, it proposed the iris dataset in 1936. These are the tutorial papers by us, which I explained. The tutorial paper on this is the paper on RDA. This is the another paper on RDA. This is our tutorial paper on LDA and QDA. This is our tutorial paper on FDA and kernel FDA. This is our tutorial paper on eigenvalue and generalized eigenvalue problems. Okay, I hope this was useful and have fun. Thank you.